Good morning or afternoon or evening to everybody watching this, and welcome to this quick lecture on the basics of data in machine learning. And today we'll be discussing some fundamental concepts that are essential for building effective machine learning models, such as data types, data structures, descriptive statistics, and probability, which is more than likely the more important one. So, as we all know, data is everywhere around us, and it's becoming increasingly important in our daily lives. In particular, data plays a critical role in machine learning, which is a rapidly growing field that has the potential to transform many industries and domains, as you've probably seen since you're watching this video, I assume. By using data and machine learning techniques, we can extract valuable insights and patterns from complex data sets and make informed decisions based on the data-driven insights. However, to do this effectively, we need to have a solid understanding of the basics of the data, including how it's structured, how it's represented, and how we can analyze and visualize it. So, in this presentation, we'll be exploring some of the key concepts in depth, and we'll be looking at how they apply in the context of machine learning. I hope that by the end of this presentation, you'll have a clear understanding of the fundamentals of data in machine learning, and you'll be better equipped to tackle a real-world data analysis problem. So thank you for joining me, and let's get started. All right, so why is data important in machine learning? Well, data is the raw material that machine algorithms use to learn patterns and make predictions, right? Without data, machine learning algorithms would have nothing to learn from, and they wouldn't be able to make accurate predictions. So the quality and the quantity of data is very important and can have a significant impact on the performance of the machine learning algorithms. So machine learning algorithms also require a large amount of high quality data to be trained effectively. And testing and evaluation of machine learning models require additional data that is separate from the training data. Additional data can be used to improve machine learning models and identify areas where they are not performing as well as you would like. So let's take a look at the different types of data that play into effective machine learning. Numerical data. All right, numerical data is the data that consists of numeric values, which is pretty obvious, such as integers or real numbers. All right, this type of data is commonly used in machine learning for tasks such as regression and prediction, which are essentially two different names for the same meaning. Categorical data. Categorical data is data that consists of discrete categories or labels, such as colors or types of animals. This type of data is commonly used in machine learning for tasks such as classification and clustering. So text data is another type of data. Text data is a data that consists of natural language text, such as tweets or customer reviews. This type of data is commonly used in machine learning for tasks such as sentiment analysis and language translation. So image data, this one's pretty cool. Image data is data that consists of digital images or videos, such as photos or videos captured by cameras. This type of data is commonly used in machine learning for tasks such as object detection and facial recognition. And if you have an iPhone, you are probably pretty familiar with facial recognition. And if you remember setting it up, it required you to hold it straight in front of your face and then move your face around and move the camera around different angles, which gives it the ability to detect your face while you are moving or while you're on a run or while you're in a moving vehicle. And the image isn't always still. So that is an awesome example of using videos and images to form a model that can predict whether the face that is in front of your phone's camera is actually you or if it is somebody else. So unfortunately, those models are not perfect, but they are pretty darn close. All right, let's take a look at data structures. All right, some different kinds of data structures. So some of the most used data structures in machine learning include arrays, lists, dictionaries, trees, and graphs. Trees and graphs are more visualization than anything, rather than practical use, in my opinion. But let's take a look at arrays and lists and how they are commonly used to store and manipulate numerical data in machine learning algorithms, typically used in matrix operations for deep learning. So here's an array. All right, you got an array of a bunch of complex numbers here that range between 0 and 1. So Right there, you can notice none of them are separated by a comma, and depending on the programming language, if you're a programmer using this, an array can be structured very differently. So a list is very similar to an array. A list essentially can contain a very large spread of different items. So it could be more lists, it could be arrays, it could be a numerical values, or in programming words, a string value or text. And many different things can be put into an array, a list, I'm sorry. So if we take a look at dictionaries, these are commonly used to store categorical data such as mapping labels to numerical values and classification tasks. For example, if we take a look at this dictionary here, we've got ninth grade. If we take a look at all the students in a high school, we can separate them in 4 different categories, which is 9th, 10th, 11th, and 12th grade. And then here in all of these categories, they each have a key value. So ninth grade has 200 and 10th grade has 180. So you can typically access these items values by just querying for the actual category name. So 10th grade would return 180, that kind of thing. So not going to go into programming a whole lot, but that's just a little idea of how dictionaries can be useful. Cool. So trees and graphs are also commonly used to represent complex relationships and dependencies, partnerships among data points in machine learning, such as decision trees and neural networks, which those two things in this lecture here. Let's take a look at graphs. This is an example of a graph, a regression model. Like I said, regression and prediction are kind of similar here. As you can see, that red line right there, and its kind of general direction that it's pointing in, you can kind of make an assumption of what's happening here. So at the bottom, you have age, and at the very left, you have your calories burned per day, otherwise known as your y-axis. So as the age increases, you can see that the calories per day begins to start to taper off. I will have to note this is completely made up data, and I just put it on a graph so you can have an idea of kind of what this looks like. This is an example of a decision tree. I pulled this off of IBM's website because it was a pretty good example of a simple decision tree, which is also kind of a similar understanding of a search tree as well in a way. But if we take a look, you've got your root node, which I like to actually make them the analogy of towards a tree. So the root node is kind of like your main trunk of the tree. Like that's the first thing that comes out of the ground. You look at the 2 internal nodes, and those are the first 2 major splits of the branch, or however many splits you could have. It could be more than 2. And you know how a tree starts to break off, and then it starts to break off into more branches and into more branches. In this case, it only branches off 3 times. And if we look at the 3rd branching, those are called leaf nodes, and that is what is at the end of each branch. So typically, the values that are going to be searched for, or the decisions that will be made based off of the data that is. So go ahead and look at descriptive statistics and exactly how they apply to machine learning and probability. So why is describing your data important? All right, so this is an interesting topic here, right? So descriptive statistics are important in machine learning because they provide a way to summarize and understand the characteristics of the data that is being analyzed. By using descriptive statistics, you can gain insights into the distribution, the central tendency of the data, and the variability and relationships between the different variables in your data, which can help you make more informed choices or decisions about which machine learning algorithm you want to use or you should use, and how you could optimize those machine learning algorithms. Now let's take a look at the first 3 basic ones, which most people are already familiar with, but we will skim over these real quick. So the mean, also known as the average, is the sum of all of the values in your data set. So we take a look at a numerical data set. If we have 5 data points and they range from 1, 2, 3, 4, and 5 in value, we would essentially add all of those together, which, if I remember correctly, is 15. And then if you take 1, 2, 3, 4, and 5, you added it up, which is 15, and then you would divide it by the number of values. And if there's 5 number of values, you would divide 15 by 5. That would give you an average or a mean 3, which can be important in the next slide. All right, in machine learning, the mean is often used to summarize and understand the characteristics of the data that is being analyzed. And for example, data preprocessing. This is not a topic we will cover in this lecture, but this is how mean is used in terms of machine learning, evaluating the model's performance, okay? and feature selection. Again, some of the things we won't be covering here for time's sake. The median is very similar to the mean, and as most of you already know, to find the mean, you first need to arrange your values in a set that they start from the smallest and work their way up to the very largest. Okay, this is a better way of finding middle ground if you have a very large spread and lots of outliers in your data set. So for example, if I have our last example, 1 through 5, if I added a sixth data point that had 10,000 as its value, you'd have 1, 2, 3, 4, 5, and 10,000. That mean is going to be very different than the median of that same data set, if that makes sense. So they can show different things depending on the stuff that you're looking for. So they are, the median is used for essentially the same stuff that the mean is used for. So in machine learning, the median is often used as an alternative to the mean for summarizing and understanding the characteristics of the data. The mode, let's talk about that. So like I said, most of you guys already know this stuff, but a nice little skim is important here. The mode is another measure of central tendency in statistics, central tendency, right? Which represents the most commonly occurring value in a set of numbers. Unlike the mean and median, which are calculated using mathematical formulas. The mode is simply the value that appears most frequently in the data set. Siri, I do not need an answer. Thank you, though. All right, so for example, in our little data set here, if we had 1, 2, 3, 4, and 5, what if we change it to 1, 2, 3, 3, and 5? In that scenario there, the mean and median would change, but the mode would be 3 because 3 occurred twice, and that is the most frequently occurring value in our data set. All right, in machine learning, the mode can be used in a few different ways, and that is going to be handling missing data. We won't cover these topics, categorical data analysis, and model interpretation. Cool. So that is your mean, median, and mode. How they kind of apply with your standard deviation and variance, which is a little bit more important in understanding your overall data and how it's working out. So standard deviation is a measure of the amount of variation or difference or dispersion in a set of data. So it measures how spread out the data is from the average value. So like I said, if we have 5 data points and our mean is 3, then you're going to check and see how all the data points essentially differ from that very center average rate there. So a high standard deviation indicates that the data points are spread out over a larger range of values, while a low standard deviation indicates that the data points are typically very close together. They're not very far apart from one another. So that is essentially how you would use your standard deviation, and the formula to calculate that, which is why the mean is important, is essentially what you would first do. All right, as you can see, SD is equal to the standard deviation. Standard deviation is equal to the square root. And now the part of this formula here is sum of the squared deviations from the mean. Now to find your squared, or to find your deviations, you would first get the mean, and then you would subtract the mean from the data points value. So if we had 1, 2, 3, 4, and 5, and your median or your mean was 3, for example, you would take 1 and subtract it from 3. Or you would take 3 and subtract it from 1. I'm sorry, I got that mixed up. So you would have -2. All right, and then you would square that, because right here it says sum of squared deviations from the mean. Anyways, that is essentially how you would do that. And you would do that for each data point until you have your total sum, and then you would take the square root of that. So your variance here can be a little bit more of a precise and unaltered version of your standard deviation. And this is essentially another measure of the spread or dispersion of a data set, which is closely related to the standard deviation. Variance measures how much the values in a data set vary from the mean or average value, just like the standard deviation. A high variance indicates that the values are spread out over a larger range, while a low variance indicates that the values are tightly clustered around the mean, just like standard deviation, very similar. So if you look at the formula here, it's very similar to the standard deviation formula. All you would essentially do is remove the square root from the equation, or the formula, I'm sorry, and you would have the sum of squared deviations from the mean divided by the number of total values that you have in your data set. Cool, and as you can see there, that's the difference between formulas. So let's take a look at probability. Probability is a fundamental concept in machine learning and is used in a variety of ways, such as building models, making predictions, and evaluating your model's performance. Let's take a look and see. Probability is a fundamental concept in machine learning that is used to model uncertainty and make predictions. In machine learning, we use probability to describe the likelihood or chance of different events or outcomes and to make decisions based on that likelihood or probability. One important use of probability in machine learning is in probability distributions. Probability distributions allow us to describe the probabilities of different outcomes in a sample space, which is essential for many machine learning algorithms. For example, in a clustering algorithm, otherwise known as a grouping algorithm, we use probability distributions to model the likelihood of data points belonging to different clusters. So I will not give any examples on that right this moment. Another important use of probability in machine learning is in the Bayesian inference. Bayesian inference is a statistical technique that allows us to update the probability of a hypothesis as new evidence becomes available. This is useful in machine learning for tasks such as prediction and classification, where we need to continually update our models based on new data that we either observe or has been given to us. The naive Bayes classifier is a popular algorithm used in machine learning as well that is based on the Bayesian inference. The I always mess that word up, naive Bayes classifier uses probability distributions to classify different data points into different categories based on their likelihood of belonging to each category. This is useful for tasks such as text classification and sentiment analysis, which is a little bit more of an advanced topic we will not be covering in this data section of this lecture. Markov models are another type of probabilistic models used in machine learning. Markov models allow us to analyze sequences of data, such as speech signals, like, I'm not going to say its name, but Apple's Siri, and stock price movements as well. So by modeling the probabilities of different states or events in the sequence, we can make predictions about what's going to happen next. Otherwise, in this presentation, the future events. Let's take a look at some probability formulas. I'm not going to cover all the use cases for all of these, but I'll give you a little bit of a simple understanding because we will be doing a little example here shortly of a probability case. All right, so probability of an event A. All right, P of A, otherwise, this is how I say it in my head, probability of A, all right, happening is equal to the number of your total outcomes in A divided by the total number of all your outcomes, okay? So the probability of the complement of A is 1 minus the probability of A. And then the conditional probability here is the probability of A given B, given meaning that you are provided that information, is equal to the probability of A and B together divided by the probability of B. And usually finding out these probabilities, there may be some idea of these percentages that you will be using depending on your data set here. So multiplication rule of probability, all right, and this is going to be the probability of A and B is equal to the probability of A given B times B. Cool. Addition rule of probability is equal to the probability of A or B, and that is equal to the probability of A plus the probability of B minus the probability of A and B. All right, so we're doing a lot of probabilities here. So not to bore you to death, I'm going to go ahead and show you this last one here. It's called Bayes' theorem. This one is pretty important. We will be using this next. The probability of H, and I will go ahead and say this if we skip that formula here, H is a hypothesis, E is your evidence, and we're going to look at the theorem's formula now, which is bolded. The probability of the hypothesis being true, given your evidence that you were provided, is equal to the probability of your evidence given that the hypothesis is true, times the probability of your hypothesis divided by the probability of the evidence. Now, this may sound like a bunch of jumble, gibberish to you at this moment, but I'm going to clear things up a little bit. Next example. So let's go ahead and suppose we have a medical test that is designed to detect a certain disease. A good one to use right now would be COVID, right? COVID is something that is still present today, but we get issues with that all the time. So let's take a look. This test is known to be 95% accurate. I just want to say this is not based off of code numbers. This is just thrown out of the blue, meaning that it correctly identifies 95% of people, otherwise known as 95 out of 100 people, it will correctly identify whether they have the disease. And it incorrectly identifies 5%, otherwise known as 5 out of 100 people, who do not have the disease, as having the disease. We also know that the disease is fairly rare, occurring in about 1% of the population. And that's kind of subjective in terms of fairly rare, because in the US, you've got 330 million people. 1% of that is 3.3 million people that either currently or have had the disease in the past. So that's kind of pretty honestly not too rare. So now let's say that we have a patient, right, who takes the test and they get a positive test result. So now what is the actual probability that that patient legitimately has that disease and that wasn't just a false positive test? Look at how we can use Bayes' theorem to solve that issue for us and to get a more concise understanding of the probability that that is true. So to use Bayes' theorem to answer this question, we need to define our hypothesis and our evidence. Okay, our hypothesis is that the patient actually has a disease. And the reason why we think that, otherwise known as our evidence here, is that the patient has just tested positive for it. So your reasoning to saying, I think they have the disease, is because you have evidence of a positive result for the disease. And once again, not every test is accurate. So that's the whole point of this example here. So we can then use the Bayes theorem to calculate the probability of our hypothesis given the observed evidence. Cool. Let's see how this works. So the probability that the patient actually has a disease, which is your hypothesis, given that the test, your evidence that he tested positive, is equal to the likelihood or probability that the patient, that you assume the patient has tested positive because they have the disease. I hope that makes sense. Okay, sometimes it can be a little bit confusing to wrap your head around. But if you take a look and you're essentially just mirroring the two, you're giving two different perspectives here. You're asking what's the probability that he's got the disease because he tested positive, and what's the probability that they tested positive because they have the disease. So let's take a look and see. So what you're going to do here is you're going to multiply the probability that they tested positive because they had the disease by the probability that the patient actually has it, divided by the probability that the patient also tested positive. All right, let's take a look and see. So if you look where it says P has disease given tests positive, all right, the probability that the patient has the disease given that they just tested positive is called the posterior probability that the patient has the disease, given that they have tested positive, okay? Some notation there. The probability that they tested positive, given that they have the disease, is the likelihood that the patient tests positive, given that they have the disease. This is the sensitivity of the test, which we assume to be 0.95, otherwise known as 95%, or 95 out of 100 people. All right, 0.95, cool. And the probability that they have the disease is the prior probability that the patient has the disease in the first place. How do they get it? So we assume that is 1%. So they had a 1% chance of getting it, and they have a 95% chance that the test is actually accurate. Now that we have a base understanding of how it works, we can take a look and see what the probability that they test positive here. And we can calculate that using the total probability theorem, which we will go over in the next slide. All right, total probability theorem. Now let's take a look and see. The probability that the patient has tested positive is equal to, this is going to be a lot, so try to pay attention here or write this down if it helps you. The probability that they tested positive is going to be equal to the probability that they tested positive given that they had the disease. Okay, we're going to put all these numbers together soon here. You're going to multiply that by the probability that the patient actually has a disease plus the probability that the patient tested positive given that they do not have the disease times the probability that the patient does not have the disease, which is 99% chance the patient does not have the disease, right? Just in general terms without looking at any evidence. Cool. So if we put these numbers to work, the probability that the patient tests positive is equal to 95% times 1%, or 0.95 times 1.01. And you're going to add that to 0.05, or 5%, times 0.99, or 99%. Once you put that together, you will get 0.058, or 5%, or 6%. All right, so now that we have that, and this is just a little reminder, if you look back at the starting page that we started with our probability example, all this information is located there, so you can see that. Plugging these values into Bayes' theorem, we get the probability that the patient has the disease given that they just tested positive, is equal to 95% times this number right here, which is 0.01 divided by 0.058. Okay, so in this example, if we look at how we need to calculate this, we can use our calculator. But if we look at PEMDAS, you want to do everything inside your parentheses, any exponents. Your multiplication is going to go first, and your division is going to go after your multiplication. So you want to do 0.95 times 0.01 and divide that by your 0.058. And then you should get 0.16 and a bunch of other numbers after 0.16. So we'll just stick with 0.163. Cool. Okay. So the probability that the patient actually has the disease, given that they just tested positive, is about 16.3%. So that's how we use Bayes' theorem to kind of get a different conclusion or rough estimate of the actual likelihood that that's true. 16.3% is kind of, it is up there for sure in terms of probability wise. That's essentially saying that 8 out of 50 people or 16 out of 100 people are going to have the test, mean that they actually have the disease. So that can be a little confusing. If you need to go back and rewatch that, I encourage you to do so, because that is going to be the fundamental idea there of the complete concept of how machine learning is going to be tied in to making appropriate predictions based off of what you want the outcome to be. So, and there's different ways to train your models and stuff like that. And a good little example there, if you think about it, think about how much work had to be put into it, how much data you have to provide to a model like ChatGPT that currently right now is exploding in order for you to be able to give it a bunch of letters and characters, and for that algorithm to take those characters that you worded into words and sentences and paragraphs and questions, to take all those letters and transform those letters into more different letters that to you looks like a response, and it makes sense, and it's informative, and it's helpful, and it does what you wanted it to do. But at the end of the day, the computer just knows to run this process. There's really no life behind the actual concept there. It's just a probable guess. Okay, this is what you probably want to hear from me, and this is the information I have. And due to some of OpenAI's alignment, which is another part of machine learning that we will not talk about during this, it can give you accurate results. So with a nice blend of supervised and unsupervised learning, which I am currently making another video for you. But that is a good little example of why probability, your data that you train the models are all kind of important and fundamental when it comes to machine learning. So in conclusion, understanding the concepts of data, data types, data structures, descriptive statistics, and probability is crucial for effective machine learning. These concepts form the foundation of the data-driven approach that is used in machine learning and data science. And they are essential for analyzing and modeling complex data sets. So by learning about data and data types, we can understand how to represent and manipulate data in a way that is appropriate for machine learning tasks. By studying data structures, we can learn how to organize and store data efficiently, which is important for processing large amounts of data. Descriptive statistics provide us with tools for summarizing and visualizing the data, especially if you got to look at it lots amounts of data sets and getting an idea of what those data sets represent. And they allow us to make informed decisions about how to pre-process and clean data for machine learning models. Probability theory is a key component of many machine learning algorithms, and it provides a framework for modeling uncertainty and making predictions based on observed data. In summary, mastering the fundamentals of data, data types, data structures, descriptive statistics, and probability is critical for developing effective machine learning models and solving real-world problems in a variety of domains, including finance, healthcare, and natural language processing. By understanding these concepts, we can build more accurate and robust models and make better decisions based on data-driven insights. So there you go. There you have it. So I hope that you learned something from this. And if you did not understand, please comment down below if I can help you answer any questions about this lecture. And I will continue to make our next video based off of unsupervised and supervised learning. And we may also be diving into how to implement these concepts into Python in our next video. So I hope that you enjoyed this. I hope that you learned something from it. If you did, please like and subscribe, because I will be continuing to put out more information just like this. Have a great day. Bye now.